I think we should, can you hear me?
Yes, ma'am.
Okay, perfect. I think we should start and see how people, maybe someone can send a note through the group me. Do you guys have access to it? I'll send a note. Okay, thank you, Seth. Thank you. Also, I got your email about the 28th, and no problem, Seth.
Thank you, ma'am.
Usually you know, you can use the makeup assignment to make up for it.
Sounds good, ma'am.
Yeah, thank you. All right, so what I decided to do today, I'm not coming with a specific set of problems, but I would like to hear from you what types of problems you would like me to solve, and whether you would like me to solve analytically or with a Smith chart or both. And then accordingly, we're gonna find the solutions. So while I'm entering one Smith chart here, where is it? So if you can think about what types of problems you would like me to solve. And I have the Smith chart here, so we can solve them either way. What do you think? It's not bad being small, it's gonna be more interactive. Don't worry, so somebody has to speak up. Otherwise, I'm gonna just think myself something. I will, do you want me to make them up myself? What do you think?
I know I could definitely use some more practice with the Smith charts.
Okay, perfect. I'm gonna get also another one because it's simpler than the red one. Let's use this one. So we're gonna solve a problem and then we're gonna do it. We're gonna take a few problems and then we'll solve them with the Smith chart and we'll be matching problems. Let me just see. Okay, here. This Smith chart, there are all kinds. Have you tried to look at for Smith charts on the web? There are all kinds of Smith charts. There are some that are extremely complex. I will not suggest going through those. Like the red one I have here is a complex Smith chart. But I will suggest that we go with something simpler. I mean, I like this one because it has multiple, if you see, but you can get confused. So we'll get this one that has simpler. All right, so now, since we are here, let's try to move this to add a page. Let's see how we're gonna do this. We're gonna add a page, perfect here. And I was thinking the following, like a matching problem. Let's try to do that. Someone is giving us the following problem. Say, consider problem 1.
Are we supposed to be seeing your iPad screen right now?
Yes, yes you are. And you don't see that. Because I have, it's broadcasted according to this one. Do you see it or not?
I don't at the moment, no.
Okay, that's interesting. You only see me, you don't, unless I have, okay. Wait for a second. I think I have zoomed into something else. Stop broadcast. There are so many Zoom sections. Okay, here. And I go here. And Zoom. Okay. So most probably I was in the previous one for the office hours. Open. Yeah, that's what it is. And then start. Now I'm on. Excellent. Okay, so now I can do screen. No, okay, so you should, at least I see it now. Thank you for telling me. So I got one Smith chart here, as you can see, and then I was talking about another Smith chart, which I have, this one, which is a little more complex because it has multiple readings. And while it's useful for that, for people who have used it extensively, I think it's not gonna do it for us today. We're gonna use the simpler one. Okay, so this one, we're gonna use what you have seen. So I was thinking the problem that we are gonna solve is the following. We have an incoming transmission line. And then we have a load. And let's assume that the load is the input to another circuit. And it's a complex load, all right? This one is Z naught. Always a reference impedance. And we are gonna use a reference impedance of 50 ohms, always. Unless something else happens and I make that reference to you. So somebody's giving us this load. It's coming maybe from an amplifier design, maybe it's the input. Okay, let me make it up right now. So I'm making up things. Let's assume that somebody said the following. I have an input line. You remember sometimes we show them only with one line when we are in system design. And then we have the bandpass filter that, let's assume that I'm coming from an antenna. I just want you to piece things together and see the bigger picture and then go down to the smaller. So the antenna is here. And then I have a bandpass filter. Bandpass filter. And then I have an LNA. And so forth, all right? So I'll give you the following problem. Somebody tells you that I have designed the LNA and my LNA has an input impedance of 100 ohms minus J20. Okay, that's how I made it. I made it and that's what I measured as an input impedance. And then, so another member of your team creates the bandpass filter and says, well, I made my bandpass filter, but the input impedance I see from the end, I made it so it connects to a 50 ohm load. So I made it so it goes from 50. All right, so when I look to the left, I see here a Z from the filter, let's call it Z1, to be 50 ohms. When I look to the other end, I see Z from the LNA. Z from the LNA, and I see that. And then let's, to be more accurate, go here from the filter. Band pass filter. So then they say you have to put them together in the system. So how would you do that? You will have to put at the center, in between the two, a matching network. Otherwise, when the power comes in from your antenna to your filter, and if my filter design is good and goes through the filter and is filtering it, but I'm not losing a lot of power, then when the power comes out from your bandpass filter and sees other than 50 ohms, then part of the power is going to go back. And so what is going to enter into the LNA is going to be less. And you don't have too much to lose, all right? Your incoming power already is weak because it's just receiving from a transmitter which is in a far distance. So if I lose part of my in into the reflected, then what I get here, it's even smaller. The transmitted, the real power transmitted, then P sub T is going to be the P incident minus the P reflected, all right? So that's what I'm going to have. So I would like to make sure that I connect the filter, which here gives us a 50 ohm. I connect it to an LNA which gives us here 100 minus J 20 ohms. All right, so what am I gonna have to do? I will have to place in between a matching network. Matching network, which is gonna have as a load this one, all right? And which is gonna have then to, that sees a 50 ohm input. Okay, so that is how the problem looks. When somebody gives it to you from a systems perspective. All right, and then, in fact, what I will do is I will put this in a square. And then I will, and this is the definition of the problem, then I will take here this one, and I will move it below it. Okay. So I start with the definition of the problem, which is in fact nothing else but to match an LNA to a filter. And now I have to develop my matching network. Okay, so practically what I have to do is to put something in between. Isabel is real, has a real part. A 100 minus J 20, all in ohms. It's impedance. I have to put something in here, which is gonna match it, and when I look this way, I see 50 ohms. Do you agree? Now, if you agree with that concept, the question is, how do I do this? And what do you think? I mean, before even we start doing stuff, before we write equations, before we go to the Smith chart, just from the things that we know, because that's how designs are done. Step by step, all right? Small steps, not big ones. So the next small step is to ask ourselves, okay, from the things that we know, how can we match a reactive load that has a real and an imaginary part to a real 50 ohms? What can we use to do that? And obviously, since we are in high frequencies, we are not gonna use just, well, let me ask you, I need to have a conversation with you to see. And then so I can bring you into the right conclusion. So what do you think we can use? And I would like people to speak up. What do you think we can use to match the complex load to 50 ohms?
Would we
Go
need a
ahead.
stub?
Yes. What will the stub do?
Like cancel the reactive part of the load?
Perfect. And then if we cancel the reactive part, what are we left with?
100 ohms. So would we need a quarter wave to transform that?
Excellent. Yes, absolutely.
Okay.
So let's try to do that, okay? So the first thing is that without even the Smith chart, I can do this quickly. What I decided to do is to use 50 ohms as my reference. And then I will do both here and in the Smith chart. So I do 50 ohms as my reference. 50 ohms is my reference impedance, always. Okay, now let's think about it. The load is nothing else but my LNA. Let me color it here for you, my LNA. Where am I gonna place the stub? What do you think?
Closer to the source than the load.
Yes, because if I place it too close to my LNA, I may mess up things. Because what happens with these circuits is, first of all, you need to remember that we have to make them. And then we have to create the layout. And usually all of these LNAs is like printed circuits. And the input will be somewhere where the LNA stops, all right? I mean, may have a capacitor in there, who knows, may have other things. So we don't wanna bring our stuff too close, our stub, too close to the LNA, because I don't know what I may mess up there. And first of all, you can never really be that close because there is always some spacing, okay? So I would have, while the solution that your colleague mentioned is absolutely correct on paper, I can put it on paper. Let me just do that for a moment to do the solution because it is correct. So on paper, what I could do is I could place here the stub, and in fact, because it's an impedance, I will place a series stub, all right? So this is just a wire, it's not transmission line. So let me in fact do this for a moment. And then my stub is gonna be like this, series stub. And if I am microstrip, I will leave it open because you remember what I said about microstrip? It's difficult to open holes in the substrate. It needs very special pieces. So I'll use an open stub. Now on paper, you can use a short too, but let me use an open this time. So this is an open circuited stub. And I put it in series because I have an impedance here. You remember that, all right? And with impedances, I sum up when they are in series. Okay. Then what we discussed before is that now we put a quarter of a wavelength transformer. And I said, yes, because it's true. I can put a quarter wavelength transformer here. And all of this is gonna be nice. It's gonna do on paper what I really want. Now, also before I go anywhere, did you see how I went from single wires that we have up here? Single wires here that I have, that I went to double wires down here, because it is two transmission lines have two conductors. Transmission lines have two conductors. Now, when, however, we do schematic for systems, we don't want the drawings to be too complex. So we drop one of the lines. We usually drop the ground, all right? And we have then the other lines there. That's why you see single lines here. But when we try to design it, really, and find the length and find all of this other thing, characteristic impedances, then we go directly from single line to double lines. So you see that. Okay, now I said I'm using 50 ohm reference. So my stub, first of all, since I'm using 50 ohm reference, 50 ohms, then the stub is going to give the following. I will write it underneath it. I still have the input line. Then I still have my transmission line. Then this one is going to give me the stub here. Is going to give me a series reactance that I do like this. Okay. And then this is going to go to the load, which is still there, the same. And then it's going to come out here. All right, so this is going to be JX. This, my load is 100 minus J20. So now I have to design the stub, which is open circuited. So the stub gives me X, JX as input. So here, for example, I will redraw the stub. So my stub looks like this, open here. Open here. So JX is what I see here towards the stub. That's JX. And the stub has a 50 ohm impedance. So if I decided that it's going to be 50 ohms, I have to find only the dimension here, the length D of the stub. How much now to find the D? I need to find X, but I know how much X is going to be because I want X to be equal, so JX to be equal to J20. Why is that? Because if I sum the two here, all right, and if I do this here, if I sum these two, and I call this Z sub T total, then Z sub T is gonna be JX plus Z sub L, which is gonna be JX plus 100 minus J20, and therefore X is gonna be 20. Okay, now let's try to work on this. In fact, JX is 20 ohms. All right, now from the stub, we know that the input impedance to a stub, so from open circuited stub, what do we know? That Z into the stub is, if it's open circuited, do you remember how it goes? Minus J Z naught cotangent of beta D. In case you don't remember that, you just need to remember the formula for Z in. I will put it here, but then I will erase it to continue. So, or then I can leave it, whatever. Z in is gonna be Z naught. That's for the stub. The load of the stub plus J Z naught tangent of beta D divided by Z naught plus J ZL load of the stub tangent of beta D. How much is Z sub LS? What is the load of the stub if it's open circuited? infinite, okay? Which makes these much smaller. So practically it makes these much smaller than 1, or Isabel. It makes these much smaller than the other term, and therefore I can ignore this, I can ignore that. And what do I get? I get the Z input to S is minus J, and then of course these two go out, minus J Z naught cotangent of beta D. All right? And now that I know Z naught, which is 50 ohms, and I know X, what do I have? I have that J 20 equals minus J 50 cotangent of beta D. And from here, I have that minus 2 over 5 is cotangent of beta D, which gives us beta D is the inverse cotangent of minus 2 over 5. And how much is that? Let's see. You guys have something easy to find it? Inverse. So there is an inverse cotangent calculator, which in fact I use, and then you give minus 2 over 5 is 0.4. So minus 0.4, done. And then calculate inverse, which gives us here, it will give you minus 68. Or if you remember, cotangent and tangent are, cotangent is a cosine over sine, all right? So if it's minus 68 and also minus 68 plus 180 will have the same. So minus 60 will have the same cotangent, because usually negative does not mean months, all right? Because it's length. So then you can go and calculate. Then you can get a calculator and then find 68.199 minus 180. That gives us beta D will be equal to 1, say 12 degrees, okay? And in fact, I can do this in radians, so divided by 360 is 0.31 times 2 pi is radian, in radians. And therefore beta, which is 2 pi over lambda, makes beta D equals 2 pi over lambda times D, and that is equal to 0.31 times 2 pi, which makes D to be 0.31 lambda. Did you see how I found the length of the stub?
Yes, ma'am.
Okay, good. That is so clear. Now, I found the length of the stub. So what do I see here with the right stub in place? What do I see there? I see only 100 ohms. Do you agree? Yes?
Yes, that makes sense.
Perfect. 100 ohms. So now, as you said, we have to create the lambda over 4, the quarter wavelength transformer, to go from 100 to 50, because that's where we're going to be. Here, 50. All right. Now, since the length is fixed, this is a quarter wavelength transformer. The only thing that we can control here is the characteristic impedance. How much this characteristic impedance will be? What do you think? Is it not that? Do you remember? When you have one line, Z naught, and then you have a load, ZL, real load, okay? Then your quarter wavelength line in between is Z1, and Z1 by definition we found, Z1 is square root of Z naught times ZL. Do you remember that?
Yes.
Yes, I remember that.
Okay, perfect. So now we have found the characteristic of impedance of the line of the quarter wavelength to be Z1 equals square root of 100 times 50, which is 5,000. And how much is that? I think that's 80 something. 5,000. If I is 70.7. So now I solved my problem. All right, this one and this one. Because now I can make this, the one that you see here in the yellow. I can make it. I found Z1 here. I found D, which is the length. And therefore I have my matching network. Okay, was that clear how we did it?
Yes.
We started with a design problem. All right, see how designs are not difficult if you start step by step. We started with this, which was a problem in the design. Then we ended up deciding we need to develop a matching network here. Then we knew the impedance. So then we decided how to do the matching network. And then after we decided how to move the matching network, then we designed the stub first. And then after the stub, we found its length. We designed the quarter wavelength line. And then we found its impedance. And that's how we solved the problem. Okay.
Could you like find the transmission matrix of that network? I think that would help. I'm definitely starting to understand this a lot better now, though, but I'm still a little confused about the matrices.
Okay, sure. So now we have found this. Let's see. So you want me to do it on Smith chart, or you want me to go to matrices? And then Smith.
Oh, if you could answer or do this problem again with the Smith chart before jumping to matrices, that'd probably be best.
Okay, excellent. So let's go to the Smith chart. Where is my? Okay, I'll add the Smith chart here. Let me move that a little bit. Do a little bit of rearranging. Okay. So here I need to add. Where is that? A lot of pictures of my granddaughter. So here. All right. Now let's try to do that. That's going to be fun. We know where our, let's remind you here. Let me remind you what we had. We had an LNA, that had an input impedance here of 100 minus J20. We had a filter on the other end that was coming with an input impedance of 50 ohms. And I saw that as, or you can put it like, since, let's do it in a way we have done for the homework problem. So we have a resistor here. So we have a filter, let me put the filter here. But everything that I see here is 50 ohms. Okay, you remember, we have that. And now the goal on the Smith chart is to identify what is in between using the Smith chart. Now we still know that with the Smith chart, we will use section of lines and stubs, we know that. And as a matter of fact, on the Smith chart, you don't, if you will see that the Smith chart may lead you into its own design by nature. All right, so we might be slightly different from the one I gave you, but it's going to be accurate. So what is going to be interesting to see is that in design problems, there's not only one possible solution, okay, which is very interesting because, and that's good, because if you find one solution on paper that works, but you cannot implement it, then you can go back and do a different solution. All right, so let's see what where are we going to go with the Smith chart. Now, you remember this is very similar to the problem. We need to start with where we are, and where we are is the 100 minus J20. So this is impedance. Let's try on the Smith chart to find 100 minus J20. But we need to normalize things, all right? Don't forget the normalization. So ZL here, normalized, is gonna be ZL divided by your reference impedance, 50 ohms. We said we are gonna use 50 ohms, which is practically 2 minus J.4. All right? So now I'm ready to go to the Smith chart. You cannot go to Smith chart without normalizing. So now I'm ready to go to the Smith chart and I find 2 minus J.4. Where is the circle of resistance that has 2? The circle that has a resistance of 2 is this one. Okay, here. Oh, kind of good. Okay, perfect. And where is our point? Is 2 minus J20, which is the normalized 0.4, minus J.4. Where is 0.4? 0.4 is here, and it's negative, so we go to the lower, okay, part of the Smith chart. So the reactive part, I'll use a different circle, green, is gonna be this one. So we have to find, in fact, we have to find, it's better if I do it like that, so that we have to find the intersection between these two. And the intersection between these two is this one. All right, that is the point. Isabel normalized. So this is Isabel. All right, from there, I want to go to, I want to do two things. If I were to go the way we did before, you would think that you will have to go from where you, because we need to go to the center of the chart, you know, don't forget that our destination is here. And usually on a Smith chart, what we did there, we changed the real part first, all right, before in the approach. But on a Smith chart, they always tell you the following. If you are to move from one point to the center, you can either move or circles that are centered at the center of the Smith chart, and they are the equal VSWR circles. So let me create the equal VSWR circle that goes through ZL. And that is going to be this one. Okay, and then I have to center it somehow. Okay. This is the constant VSWR circle that goes through ZL. What does that mean? That means that if I have a transmission line next to my LNA and not the stub, then I can only move along this line. All right, I can go. And in fact, since I'm going from the load towards the generator, you see this here? Load towards the generator, because our load is the complex ZL, and we go towards the 50, then you can only travel along this direction. I'll do it. I'll do this one. You can only travel like this along this circle. Now, how long am I going to travel? I know that I have to put a stub. But if I put a stub, the only thing that I do is to change the real part, all right? And I would like to get here, so the only place where I can stop and place the stub is here. Because if at this point I stop and then I place a stub, the only thing that the stub will do for me is to change my reactive part. So it's going to keep the resistance the same, which normalized is 1. So practically what I do is I travel on the constant VSWR circle like this. And then I travel on the constant resistance circle, which is 1 now, all right, here, and then I come to the center. So practically, I have 2 paths. I have path 1 that tells me that I have to travel along a transmission line, so I have to put a section of a transmission line, and then I travel along this path, P2, that tells me that I have to put a stub. Any questions so far? Okay. In reality, now I can find the following 2 things. I need to find the length of the line, which is by looking at path P1, and I need to find the length of the stub by looking at path P2. And I will explain how to do that, but in the meantime, I will also describe what we've done. So here, we had a load at the end, which is the low noise amplifier. And then in the Smith chart, the easiest thing that I did is not the same one that I put on paper analytically. That is a different one. Is one that starts with a transmission line and ends with a stub. All right, and then here we'll end with a stub, and we don't know yet what stub we have. We are gonna, but we know that we have a section of the line, and that's what I said, coming from path P1. That's my transmission line. I'll tell you when we will know about the stub. So this is gonna be path P1, And this transmission line, since everything is normalized to Z naught, obviously we expect it, wherever you get transmission lines on the Smith chart, you expect them to have a characteristic impedance of Z naught. So the only thing we need to find is the length of this line, L. Now, how are we gonna find the length of this line? Here is what we are gonna do. We are gonna connect the center of the chart to ZL, and then the center of the chart to this point. Let me call this point A. This point A is practically here. And let me call, and this other ZL is where the point B is, where ZL is, all right? Let me call that point B for now. Point B, we don't have too much space. That's why I erased ZL. So point B is right at the load here. All right, as a matter of fact, what you're gonna have on a 2-line configuration is this one. That's what we normally have. So at point B, we have ZL. At point A, we have arrived at the end of the transmission line. Okay, now what we're gonna do, we are going to write, and I'm gonna use some other colors. I'm gonna write a line that connects the center of the Smith chart to B. And I'll take it there. And then I'm gonna write another line that will connect the center of the Smith chart to A. So, same. I did not take. Let me try it again. Okay, so there. And then I'm gonna read out, you remember we moved this direction, as I said. We moved this direction, all right, for P1. As a matter of fact, with the right color, it's this. We went from this point here to this point there. And so we have to find how much is the distance between the 2 points. Okay, so I can, in fact, for simplicity, I can put here B prime and then here A prime. So let's see, what I read from here is 0.26, about 0.27. So here you see I'm reading at the out circle, all right? So the out circle, it gives me at this point, 0.27. And when I read here, I see 0.34, 0.35, 0.34246. And this one gives me 0.346. Then I take the difference between the two, and that gives me, so for L, practically, I have to find this distance. Okay, so I have to subtract 0.346 from 0.346, 0.27, which gives me here that gives me here that L is 0.076 lambda. So I found the length of the line. Now, I need to find the stub. So I found the length of the line, all right? 0.076 lambda. Now I need to find, what do I do? How do I do this? Then I go along the line. Let me in fact use this if I may. Okay. Now, I will draw this line here. I will draw this line of the reactance that goes by A. Okay. This number, what is this number? This number is 0.7. So if I measure this, what is the problem is? That's 0.7. What is this 0.7? This is reactance. And in fact, because it's in the lower part of the Smith chart, this is minus J.7. When I move from A to the center of the Smith chart, that's where I meet the filter. All right, that's where I find 50 ohms. So if I am at point A, I have to add a J.07 to go to 0. All right, I have to add it because A has a negative J.07. So how am I going to find this? I'm going to start at this point. Now, what kind of a stub do you want? Do you want a short or an open stub?
What do we do? Open?
Open. If it's an open stub, what is the impedance going to be? Infinite. So the end of my stub is here. That's the load in my stub, infinite impedance. And I have to move along the stub, the length, until I find this point, which is 0.7, because at this point, the input impedance of the stub is gonna be J.7, which I need to move from A to O. So I will have to move all of these, and let me make it even there. I will have to move all of this distance around, all of it, until I find this point. Okay? And that length, if I want to measure it, again, I will have to connect O to the load, which is here of the stub, and then O to the end of the stub, which is here. So I have already connected O to the beginning of the stub. There is a line there. Now I have to connect O to the other end, and I will do this. Okay, it goes there. Okay. All right, now this one, let's see what it says. We have started here, if you remember. We have started here, right? And we have to move all the way until we arrive here. What is the number we measure here? Is 0.25. If we go all the lower part of the Smith chart, we arrive at 0.5. So we do already a quarter, all right? And then from 0.5, the counting starts again, and it goes from 0 to 0.09246. And then so the total distance here for the stub, if it's open circuited, is gonna be all the half of the circle, which is a quarter of a wavelength, plus plus 0.096. Okay? And this is going to give us a 6, 4, 3 lambda. So practically what the Smith chart told us is that we start with this section of line, which is very short, all right, you see, and then we put a very long stub, and the stub is open. Now, if I were, and then everything here is 50 ohms.
It's 6 o'clock.
Now, if I have 50 ohms here, all right, I can put a section of line of any length, and at any point later, it's gonna still give me 50 ohms. Do you agree with that? So I don't have to stop my matching point here next to the stub. I can put any, as it suits me, I can put any section of line here, because if I have a load here of 50 ohms, then any section of line is going to give me, a 50 ohm characteristic impedance is going to give me 50 ohms. Do you agree? So after the matching network to the left, I can add whatever length I want. So we are not going to discuss here in this design, but in any case. Now, so we found for an open circuited stub that the length is this. Now, let's see if the stub were to be short-circuited. If the stub were to be short-circuited, where would you start?
Left-hand side.
Exactly. I would start here. And then I would only have to go by this much, which is practically, it's 0.096 lambda, all right? Or L, 0.096 lambda. Okay, now let's see when are those important. Now I'm trying to tell you what frequency. I have not talked to you about the frequency yet, all right? Let's assume that the frequency, in gigahertz, that you are around 2.5 gigahertz. Let's assume that this is part of a Wi-Fi receiver. So you are now at frequency of 2.5 gigahertz. How much is the wavelength there? Lambda, free space wavelength, all right? At this point, it's not exactly, if you use microstrip, your wavelength is gonna be a little smaller. But now, let's assume that we are in free space. So the wavelength to, you need to remember, the wavelength to 1 gigahertz is 30 centimeters. So the wavelength to 2.5, how much is it gonna be? 30 divided by 2.5. Do you agree? Yes or no?
Yes.
Good.
Yes.
Okay.
Hey, I have a quick question.
Yes.
How did you know from the Smith chart that the stub would be connected with the shunt configuration as opposed to series? Aren't we looking at an impedance chart instead of an admittance chart?
Ah, you are right. Thank you for telling me. So the stub is series. Oh, thank you. Perfect. See, I took it. Yeah, the stub is in series, of course, because we have impedances.
So I guess it's just kind of like based on
Absolutely. Yes, yes. Thank you. Thank you. Thank you for doing that. You guys, I really am thankful for doing this. So, because also it helps me, first of all, it shows that you are participating and it helps me find mistakes. Okay, here. Okay. All right, so let's try to do this. So very similar. So this is very similar to the previous solution we had. The only thing is that we put the section of the line first. We changed the real part by moving to become 50 ohms, and then we put the stub to cancel the reactance. Okay, so now let's try to realize them. What we found is L. We found that L, which is the line, is 0.076 lambda, and we found L1, which is the stub, or LS, maybe. Did I have it here, LS? No, I got it LS, okay. LS for the open circuited stub, which is, what did we say, 0.346. 0.346 lambda. How much is this gonna be at 2.5 gigahertz? 2.5 is going to be 0.076 times 12, which is 0.9 of a centimeter, which is gonna make it 9.12 millimeters, the line. And how much is this gonna be? 0.346 times 12, that makes it 4.1 centimeters. Okay, now you have to realize that. So you have a circuit of an LNA that will probably, in terms, it's gonna look like at most 0.5 of a millimeter by 0.5 of a millimeter. And with the packaging, maybe it's gonna look 1 by 1 centimeter. Because the packages usually, you know, you have the LNA here and then there is packages and there are lines. They put them in packages to protect them. So let's assume the package is 1 centimeter by 1 centimeter. 1 centimeter by 1. Okay, your transmission line next to it is gonna be 9 millimeters, like another 9, almost that, 9 millimeters. And then your series stub is going to be, in fact, series, it will have to, yeah. In fact, it's very difficult to do series in microstrip, but doesn't matter. Let's assume that you have another one. Now we want to look at the lengths. And then this one, which is going to be a series like this, and it's open, okay, is going to be 4.1 centimeters. How do you think this is going to look?
Huge.
Horrible, right? Yeah, because in reality, you want to make everything so that you can materialize it. And so it's going to be difficult to do it like this, which means that I will have to remove this. And as a matter of fact, it's going to also look kind of weird the way you will have it, because it has to be the way to connect a series in microstrip is kind of tough. But in any case, the length is unacceptable. All right. So now what other options do we have? Since this we cannot do, we'll go back to the Smith chart and say, okay, let's look at the other one, which is short at one end, and then I can have it shorter than the previous. So it's 0.096. So with 0.096, how much is this length gonna look? like almost like the other one, all right? A little higher than 1 centimeter. So 0.096 times 12 is about 1.1 centimeter, which is very similar to this one, to this. So then I can print it like that. So I can choose, but I will have, of course, to make it short. But I can choose to create that kind of arrangement. Now, we have not brought yet some other issues of layout, which eventually, you know, you do your designs, and that's reality in design. You do your designs, you do them on paper, they all look good. You try to do your layout and you cannot. And so I will explain to you why doing the layout with microstrip. There are two types of transmission lines we can use. There are transmission lines that look like microstrip, and they are equally used. They are equally useful. That looks like that. And then, in fact, in 3D will look like this, all right? So the difference between a microstrip and a coplanar waveguide that looks like this. So coplanar waveguide has all of the metals on one side. And when you look on top, it's gonna be like this. So practically in a coplanar waveguide, if this one looks like this on top, the microstrip, if you look like here, in a coplanar waveguide, when you look like that, it looks like 3 metals, the center one, and then 2 larger metals. Theoretically, they were infinite, but of course, nobody's gonna print an infinite metal because it creates other kinds of problems. So usually, the 2 outer metals are finite, but bigger than the center one. Looks like this. That's a coplanar waveguide. Now, what happens when you use microstrip, and what happens when you use the coplanar waveguide? The coplanar waveguide, because both conductors, ground here, and signal line are all on the same surface, ground, ground, and signal, it's easy to short circuit things. And it's easy to put something in series. Okay, so for example, let me put here a series shorted stub in coplanar waveguide. So how would I materialize our solution in coplanar waveguide? Will be as following. Let me use this one, and I will use it a little thicker to make the, this is the inner conductor. And I will use this one for the outer conductor. This is coplanar waveguide, all right? And I would like to put in series a shorted stub. How is it gonna look? My shorted stub in series is gonna look like this. I have to do it symmetric on both sides. That's a shorted stub. Do you see how it is? You take the center, the signal line, and you short it to, of course, you short. This is a short. It's a short circuit rather, as opposed to being a stub in this particular case. But it's a short. So it's easy to short things on one surface when you have a coplanar waveguide. Now, what happens with a microstrip? The microstrip, because you have your conductor on one line, what it's easy to do is to create something and leave it open, all right? Because your metal is on the other side. So if I do something like this is gonna be like a series stub. The conductor is on the other side, but it's open, okay? So the easiest thing to do is gonna be a series stub, but sorted in microstrip. So series but sorted in microstrip. And here parallel, but excuse me, open, sorry, not open, in microstrip, parallel but sorted. In CPW, coplanar waveguide. That's microstrip. So now, if we were to design our, since I discussed that, if we were to design our microstrip, unfortunately, to avoid the 4 centimeters, we would have to create a shorted stub in a microstrip, which means that you will have to go here, if it's that short, to go here and open a hole. You will have an open hole, and if you do it in lower frequencies, it's okay, but it's difficult to do it high frequencies. You have to open a hole, which practically in 3 dimensions is gonna look like this. Your microstrip, here, the ground, and then you will have this stub extended here, all right? This is still your microstrip here. Series connection. And then here, you're gonna open a hole and you're gonna connect it to the ground, and the ground is gonna go like this. Do you see what I'm more or less saying? Can you visualize that?
I have a quick question about the coplanar waveguide.
Yes.
How do you measure or how do you design the lengths of the stub? It seems to me that it's kind of a fixed length between the signal plane and the ground planes. How would you, I guess I'm just not seeing that correctly. Is it like the width maybe, or?
The thickness. So what you
The
design.
thickness, got you, okay.
Yeah, this is the thickness. The length of the stub is this one. That's the thickness. All right? This is the thickness of the microstrip. We are gonna cover this more extensively, but I wanna tell you now, this is the thickness of the microstrip, this is its length. The stub comes out, you know, like here. See, the way we have a series stub, one line, you know, comes out. And then it's they are sorted here, and then there is here. Now here, you see that? With the short, it would look like this, all right? So it's in microstrip form, a series like this. It's something like what you see here. And shorted is gonna make it like that. Now, the width of the microstrip is gonna help you with the characteristic impedance of the microstrip. So if you have the thickness, which is fixed, to find the characteristic impedance, you would need really to use the formulas, which from the thickness of the substrate and from the width of the microstrip, you can find the characteristic impedance, or if you know the characteristic impedance, you know what the substrate thickness is, then you find the width. I have to say though, one thing, that we don't plan in this class to do layouts. So a lot of the designs we are gonna have will be generic on transmission lines, all right? Because to try to do layouts is bringing one other level of complication that we don't have time to deal with. So I'm just giving this information to you as we solve the problem to see why short and open might be useful at times and why some lengths may not be as good as other lengths. All right, so you just realize that, but we're not gonna have to do layout for our project here. I'm just giving it to you as a piece of information. So So that's how we lay out things. Any other questions? I will try to shape this up before I will put it out there, but I just wanted to tell you that there are specific things that are difficult to do in some geometries, and then some other things that are easier to do. So that's what I wanted to describe. Any questions? Okay. How does this all look to you? Is it too heavy?
I like the fact that you brought in design as opposed to just numbers and letters.
Okay.
That you actually made it really applicable.
Yeah. Okay, that's important, because for the project, even if we're not going to do layout, as I said, in design, I mean, if you have geometries that are way too big compared to your wavelength, and your wavelengths are small, and you want to do a Wi-Fi for home, you cannot make, your designs to be too big. Who's going to have like a huge Wi-Fi anymore? I mean, if you see the Wi-Fis, you just plug them in on the wall. They're very tiny, even if many of them operate at 2.5 gigahertz. So people found ways to do very nice compact designs by keeping the length small. So these are important things to have, right, for a class like this. Okay, then we can continue. I think, we have some more time. What else? We have 10 more minutes. What else would you like me to do?
The transmission matrix would be good.
Ah, yes. Okay, let's go to the transmission matrix. I will redraw those things before I put it there, so I don't like those schematics the way they're a little confusing. But I will start with the transmission. Do you like to do the transmission matrix square on this circuit? Where would you like to do the transmission matrix?
Yeah, for the matching network that you have there.
Okay.
Okay.
We'll do it. What if we do it on this one? Or do you want to do it in the stub? Okay. Let's try to do it from the beginning, all right? Let's assume that you have designed your matching network, or somebody's giving you a matching network. How about that? So let's assume that I'm giving you a matching network that has a load that has been designed for this load, ZL to be 100 minus J20, and to bring it here to 50 ohms. And that is your matching network here. And people are telling you that your matching network incorporates the following. It has a section of a line, as we found it, section of a 50 ohm section of line. And we found that to be if I remember, 0.076 lambda. And then we found that it has a series stub. Or they give it to you. They give you a series stub. I have to put it out. Okay. Okay. And they found the length here. And we said, let's assume that we said it's short for this to make the length D to be 0.092, I think, lambda, or something like that. Now, and then you want to find the equivalent circuit for that, all right? the best way to find the equivalent circuit is, so somebody's asking you about your equivalent circuit. So the best way to find the equivalent circuit is to start with A, B, C, D, and then from there to find the Z11, Z12, Z212, Z22. Clean this up here. And then from there to find the equivalent circuit that is going to look like this. And this is going to be Z12, Z11 minus Z12, Z22 minus Z12, all right? So find the ABCD. Here is what I was gonna do. Instead of the stub, I was gonna replace the stub with its equivalent reactance because it simplifies it a little more. So if I were to do that, then I still have this coming line 50 ohms. Then I have this reactance here, JX. Then I have this section of the line. And then my load. Okay, now the matching circuit is like this one. And let's assume that this is port 1, this is port 2. So we have V1, I1 equals A, B, C, D, V2, I2. All right, and we need to find the ABCD. Now, what do? I cut this into two smaller pieces because my book gives me the transmission matrix for this one. And then it gives me the transmission matrix for this one. So practically my transmission matrix ABCD is nothing else but the product of two transmission matrices. A, B, C, D, let's call it stub, times A, B, C, D of line. Do you agree? And then, if you agree with that, you go to the book. So I always try to find the simplest way of doing stuff. I don't want to repeat. I don't want to rediscover the wheel. So I'm going to the book, pages 208. What did we say? Okay. I'm going to the book, pages 208, and I find the following. I find that for this one, and in fact, let me use not this color yet. I will confuse you. So for this one, which is in reality my series stub, then the ABCD matrix is as following. A equals 1, B equals JX, C equals 0, D equals 1. So that's it. Then I go to the section of the line. And for this one, the transmission matrix is the following. A equals cosine of beta L, where L is the dimension of the length of the line. B equals J Z naught, this is a knot, sine beta L, C equals J Y naught sine beta L and D cosine beta L. Then I have to take these two matrices and multiply them. So the total A matrix that I have is gonna be A will be AS, AL, AL, plus A plus Y plus A S, no, plus BS C L. This one. Okay. So AS is 1 from here. That's right here. AS. Okay, so we can separate them. And then here, what do I have? 1 times cosine, so it's a cosine beta F plus Jx, which is Bs, times Jy naught sine beta L, which in fact gives us cosine beta L minus x over z naught sine beta L. That's 1. And then you go and do the rest, all right? And after you find all of the A, B, C, and D's, then you apply the formula I gave you up here to find the Z matrix, and then from there the equivalent circuit. Is that clear for the process? Yes or no? I don't hear anybody.
Yes.
Okay, good. Otherwise, I have no feedback other than my own voice. I think that's already a lot to digest. So I would stop here. I will download, of course, this recording, the session, and then I will just fix that a little bit and upload it. Any other questions, last minute questions?
I don't have any, but thank you. This helped.
Okay, thank you.